Welcome to the sixth talk of the colloquium on artificial intelligence research and optimization. Today, we have Dr. Vijay Gadepally, and he will talk about fast AI, enabling rapid prototyping of AI solutions. And before he starts his talk, I will quickly read his bio so we know a little bit more about him. And Dr. Vijay N. Gadepally is a senior member of the technical staff at the Massachusetts Institute of Technology, Lincoln Laboratory, and works closely with the Computer Science and Artificial Intelligence Laboratory. And Vijay holds a Master of Science and PhD degree in Electrical and Computer Engineering from the Ohio State University, and a bachelor degree in Electrical Engineering from the Indian Institute of Technology, Kanpur. And in 2011, Vijay received an Outstanding Graduate Student Award at the Ohio State University. And in 2016, Vijay received the MIT Lincoln Laboratory's Early Career Technical Achievement Award. And in 2017, Vijay was named the AFC-EAS inaugural 40 under 40 list. And Vijay's research interests are high performance computing, machine learning, artificial intelligence, and high performance databases. And yeah, welcome Vijay, and we're looking forward to your talk.
All right, Patrick, thank you so much for the invitation and the introduction as well. So before I begin, I just wanted to kind of set the stage for what I'll be talking about today. So as Patrick mentioned, I'm at MIT Lincoln Laboratory, and I'm within the Lincoln Laboratory Supercomputing Center. And so within the Supercomputing Center, I lead a lot of the research efforts of the Supercomputing Center, which has grown significantly over the past few years. And so today, what I'm going to be talking about are a set of projects that all fall into this more broad umbrella of developing technology that can be used to enable rapid prototyping of AI solutions. However, before I really jump into it, I wanted to be sure to thank a number of people who have contributed to this. I would love to take credit for all the amazing work that's in this presentation, but there's really just a lot of people who have helped, who have done some of the work, as well as who have helped put these slides together. So, and these people are across Lincoln Laboratory, MIT, even the US Air Force, and of course, a big thanks to this series of sponsors who have helped make this work possible. Before I begin, I just wanted to give a brief overview for those who may not be familiar. So Lincoln Laboratory is a federally funded research and development center, often referred to as a national lab, for the Department of Defense. We work in a number of critical mission areas which roughly align with strategies of the Department of Defense. And within that, the Lincoln Laboratory Supercomputing Center is where a lot of the big computing happens. And so within LLSC, or the Supercomputing Center, we build energy efficient supercomputing that provides data centers, hardware, software, and we like to pride ourselves as being far more productive than standard supercomputing, and also more performant than standard cloud computing. So that's a very brief overview of Lincoln Laboratory as well as the Lincoln Laboratory Supercomputing Center. Next, what I wanted to talk about is in this general realm of artificial intelligence and high performance computing, we do a lot of work within the center and a lot of the folks on my team to actually go out and look at national trends to better understand where are the areas that the nation, MIT, Lincoln Laboratory, what are the types of research problems that we need to be addressing. And so these national trends are often highlighted in different reports that people put together, often where we might put together a report. And there's of course, a lot of technical research that's been going on. And so just to highlight a few of these national trends and needs that are specific to AI and supercomputing. So I'm sure many of you are aware that there has been a wide proliferation of computing platforms. And so the trend is to have different types of systems that are out there, and observations are that there are many advantages and disadvantages to picking different technologies. If we look at one of the challenges which we deal with very closely, which is in computing performance, one of the trends, of course, that many of you are probably familiar with is the end of Moore's law and Dennard scaling. And what that really means in sort of the observation we're seeing is that there's been a wider proliferation of new hardware, such as accelerators and custom processing. And there's many other challenges. I'm not going to go through all of them here today, but many of these challenges that we've seen, especially over the past few years, have really changed the way that we think about how we do high performance computing and how we make these tools available to our end users and people who leverage our supercomputer for their work. But one thing that we've seen that's come across all of these national needs and trends is that supercomputing or high performance computing is critical to world-class research and AI. So as a supercomputing center, we focus in three broad areas. The first is on interactive supercomputing, and this is really on making sure that people who use our resources have access to high performance storage and compute. We do this through application interfacing, modeling, and benchmarking, and we make available some pretty significant supercomputing infrastructure and software environments. A lot of the research, especially in the past few years, has been focused in the second area, which is on AI and big data technologies. And this is really on developing new database architectures, databases, and graph processors that can be used for people to build architecture analysis, benchmarking, and advanced mathematics. And what we do is we provide new types of infrastructure, interfaces, and processing standards. And I'll talk a little bit more about that today. But I also just wanted to note that as a supercomputing center, we also have a significant effort in education and outreach. And so this is really on providing online education and knowledge transfer, getting people using complex supercomputing system and being able to run their supercomputing or AI jobs as effectively as possible. All right, so with that, I'm going to jump into some of the AI enabling high performance computing, and then talk specifically about one of the projects that we have in my group called Fast AI, which really focuses on building new interfaces for computing, data management, and novel algorithms. And there's a lot that's going on in these, so I'll be jumping over a few details here and there, but we've published extensively on these. I've cited references. So if you'd like more details, you're more than welcome to do that, or hang around towards the end and you can ask me some questions about some of the research and maybe ways that you'd be able to join or participate in the research. So when we talk about AI, right, I'm sure many of you have seen a version of this slide before, but why is AI a thing now? And when we kind of look at it and look at the trends and look at what's been going on over the past few years, it's really the convergence of big data, heavy compute, as well as machine learning algorithms. Now, many of the folks in the audience might say, well, a lot of this has been around for a while, and that's certainly true. But I think what's really brought AI to the forefront over the past, let's say, 5 or 6 years is this convergence, all of these happening to happen right around the same time. And so when we think about AI, this is a chart that sort of illustrates what the various components are within an artificial intelligence solution. Obviously, when we talk about AI, we want to be very broad. So we're starting all the way on the left side of this slide. We have sensors and sources. These sensors and sources can be represented by structured data, such as data coming from different sensors, or unstructured, such as written notes, maybe Facebook, news articles, stuff like that. Typically, the first step you have in an AI pipeline is to perform some sort of data conditioning or conditioning. And this could include things like labeling the data, maybe doing some data curation and integration, maybe data discovery, those kind of things. Once we have conditioned the data, we've typically put it into a form that makes it amenable to apply different types of algorithms on this data. And now when we talk about algorithms within the context of AI, we're typically talking about machine learning, but just wanted to note that there are algorithmic techniques outside of machine learning that also fall within the umbrella of AI. Now, typically, once you successfully applied the algorithms on your data, you then have to step through that symbiosis or that teaming between the human and the machine. And so and there's a huge spectrum over here, right? So as an example, something like spam filtering is largely done by the machine, but there might be other applications that are more life critical, such as say in the medical domain, that have a much larger human component to it. So maybe the computing system or the AI system is providing some sort of feedback or guidance, but really it's the human that's making the end decision. Now, all of this is then passed to end users and missions. Now, when we think about all of these different pieces, they're typically run on some form of modern computing. So this could be CPUs, GPUs, or maybe more accelerator styles, such as tensor processing units, or even cooler stuff like neuromorphic or custom processors, or obviously we have to mention quantum here. And certainly, especially when we think about some of these safety critical applications, we want all of these to be built on top of a bedrock of what we call robust AI. And this includes things like explainability, metrics to understand how well or badly your system is performing, verification and validation, security, as well as policy, ethics, safety, and training that govern the usage of this AI system. Now, in all of these components, one thing that we've realized is that high performance computing plays a huge role, and it comes up in many, many places. So the first could be in defining the problem itself, right? So this is sort of that initial data curation, data conditioning part of it, where you're just starting to explore the data. It is not uncommon for people in our center and even ourselves to collect terabytes and terabytes of data to then, to just collect the data, and then you want to be able to go through it and find out what's happening. Another place where HPC plays a large part is on aggregation of lots and lots of data. As I mentioned, data sets these days in the tens to hundreds of terabytes or to even to the petabytes is not uncommon, and you really do need a high performance computing system in order to do that. Now, that was just talking about some of the data storage, but certainly if you want to create the full training and testing solution pipelines, you need a significant amount of compute. Take an example of a pretty popular model architecture like the ResNet. That's over 10,000 petaflops in terms of the amount of computing needed. So if you kind of do the math, if you tried to run that on your laptop, it'd be years for you to train that network. And certainly, training a network is not a one-time affair. You typically need to do iterations, you need to do model development, tuning, optimizations, and that's where really the amount of computing that you need explodes significantly. And so when we look at how people are using our high-performance computing system to do AI, these are the types of tasks that they are typically doing. So I just wanted to, I always like to do this with folks, but just to give people an estimate, right, to help them understand how much computing goes into a single training run. So again, this is meant to be notional, more illustrative in purposes. People, with a hardware background could probably argue with me, but this is meant to be sort of an order of magnitude. If you're trying to compute an order of magnitude of, how much computing is needed by a specific neural network model, this is a fair estimate, and sort of how I mentioned that you need over 10,000 petaflops to train ResNet. So many of us are familiar with this overall formulation of a neural network. This equation here represents the relationship between the output of layer L+1 and the input to that layer. And it basically says that the output y at the L+1th layer is some nonlinear function h being applied on the inputs or the outputs of the Lth layer multiplied by weights of that Lth layer plus a sort of associated bias term. Now, if you sort of translate this into computation that your computer would need to perform, this is what it would look like. This translates to the number of additions and multiplications per forward pass, the number of floating point operations per second per add and multiply times the number of operations per forward and backward pass. And so really deep networks that can become pretty large, times the number of training examples and the number of epochs. So if we were to really look at why is this exploding, if you just take the first part of that equation, that roughly translates to the types of models that people are using. So I mentioned a ResNet, for example, that has, tens of millions of features that you're trying to train. So that third part of that equation becomes pretty large. And then if we look at the second half of that, that roughly translates to the type of data sets that people are performing this training on. And so if we look at some of these popular data sets out there, we can certainly see an explosion in the size. So this corresponds to the number of training examples and also roughly related to the number of epochs which to get to convergence. So that's if we talked about why HPC or high performance computing has become pretty popular these days and become pretty important for developing AI. This is sort of a more rigorous reason why people have come to HPC in order to work on it. So one thing that we realized is if you really want to accelerate AI, you need to have optimized implementations, distributed algorithms, as well as hardware innovations. And if we look at if folks here are from a more traditional high performance computing background, there's a lot of the change in workloads, the change in the way people are using our system has also led to a change in the way we deploy different technologies in the system. So again, I'm not going to go through this entire slide, but just wanted to highlight a couple. One is there's been a move of the types of programming environments or languages that people are using. So where it was not uncommon when I was in grad school to program using C, C++, using MPI for distributed memory and OpenMP for shared memory parallelization, most people who use our system don't do that anymore, right? To get, they might start with Python, but they'll probably jump into something like TensorFlow or PyTorch or MATLAB or Julia pretty quickly. If they're trying to parallelize, they'll probably use one of the frameworks like Horovod, which sits on top of these. But they're not, most of our users are not generally programming at, message passing or even really working on shared memory systems. Similarly, a lot of the software that we had worked with in the past was really designed to be used on clusters, and they behaved well on clusters. And nowadays, we're finding ourselves translating software packages that we run on our laptop and trying to get them to run on a high-performance computing system. And so there's lots and lots of other changes. So one of the big things that we've done in order to make our high-performance computing system more interactive and more amenable to high performance computing jobs is to make our system interactive in nature. And so by interactive, what that means is you log on to our supercomputer, you have access to Jupyter Notebooks, Jupyter Lab, all of the machine learning, the popular machine learning libraries that people are using on a day-to-day basis. They're sort of just available and deployed on all of the nodes. Our system is 100% interactive, which means that you can easily get processor cores or sets of nodes sort of instantaneously. On the same system, we have databases that people can then store their data in. They can do data conditioning there. And we've written wrappers around some of the popular parallel programming paradigms maybe used in the cloud world like MapReduce, and then translated them to working effectively and efficiently within a high performance computing center. And finally, we've also put in online education as well as dynamic web services, because we found that people being able to learn on the same platform that they're using to do some of their research is pretty important. And we've also realized that a lot of people's end result is often distributed through web services. So we wanted to make it easy for them to start these web services on our supercomputing system. So that was a very brief but whirlwind tour of a little bit of the way we deploy our high performance computing systems in order to make it easier for people to develop AI solutions on our system. But now, however, I'm going to jump into a little bit of the research that we've been doing, and I'm certain that a lot of this will open more questions than answers, and I'm happy to take any questions towards the end of the talk that you may have. So, all right, just a reminder, here is the architecture I talked about on when we think about AI, so everywhere from sensors to the end mission. With data conditioning algorithms, human machine teaming, modern computing, and robust AI. And so over the past few years, my team has been building a pretty significant research portfolio on building rapid prototyping tools that people can use to develop and deploy AI. And this is split into 3 pieces. The first is on extreme computing. And this is how do we get people access to new AI computing hardware, and how do we do some of the performance optimization in order to bridge that gap between what deep learning needs from a computational requirement and where processors are going today, right? As I mentioned earlier, there's the end of Moore's law has started to really taper off the amount of performance gains we could get from just sort of churning the time on hardware development. And so we need to look for additional room for optimizations, both within a single processor, but across processors as well. The second area is on massive data, which is how do we reduce the amount of time that people are spending doing data collection, cleaning, and pre-processing. And I think by some accounts that takes up like 3/4 or 80% of the time people are spending on building an end-to-end AI workflow. And what that really means is that that is time spent, that's time wasted from solving the actual problem, right? No one's getting kudos points for just aggregating two data sets. You typically want to do something with it. And so that 80% of the time that you spent trying to look for outliers and remove that and put it all together, that's really time wasted where you could have really spent it on solving a real problem. And so in order to do that, my team has been building curated repositories for AI data, but also been building new tools for data management that make it easier for people to store, process, integrate, clean these heterogeneous sets of data. And finally, along the interfaces and algorithms, as I mentioned, we work with the Department of Defense, but we've seen this across many other organizations, that you need to have access to diverse, robust, and transferable AI. And so in order to do that, we've been building optimized software tools that can be used for the broadest set of applications. And so our team has really been enabling rapid prototyping of these various types of AI applications. So I'm going to just jump through each of these really, really quickly. So the first one's on modern computing, right? As I mentioned, extreme computing is driving next generation AI, and there's many, many different choices that are out there. And a decade ago, this was not the case, right? There was a smaller set of both manufacturers as well as hardware platforms that people could use. We've just seen an explosion of that. And each of these hardware platforms have different characteristics associated with them. So this is actually a chart that one of my colleagues has been putting together to essentially measure and follow different types of neural network accelerators and how their performance has gone over the past few years. And he continues to update this slide as new and new entrants come up. And I can tell you that this slide has gotten really, really busy these days, because there's just almost every day seemingly there's a new player or a new entrant into this hardware, into this machine learning accelerator space. So what we have over here is on the y-axis is the peak gigaops per second. This is measured where possible, or based on some calculations from the white papers that people are presenting. And then on the x-axis, we have the peak power. And so what we're trying to show over here is that there are a lot of processors coming up, and we can't necessarily compare all of them apples to apples. So on one end, you might have something like a neuromorphic processor, like the True North, which is, you can read some pretty interesting papers about, which has overall lower peak gigaops per second, but also at a much lower power envelope. But then if you go all the way to the top right of the slide, you see things like NVIDIA's DGX2 and DGX1. These have really high, these are data center level chips, but also with a very significant, also have very high power usage as well. So depending on the application that you're doing, you might choose different hardware platforms. And that's what we're really trying to lay out over here, that there are different choices depending on what your application is. And then there's also a lot of other details that are in this slide that I won't probably go through today, such as what type of precision is supported by these processors, what is the form factor, is it just a chip, a card, is it a full system, and what type of computation does it support? Can it support both inference and training, or a trend is also for a lot of these accelerators to support inference only. So if you kind of look at this slide for a little bit, you'll be able to see all those distinctions. So we're not trying to say that anyone's better or worse. They all have different parameters, but they all fit into this space. But what it is a big challenge for people who are trying to determine what is a suitable hardware platform for them to deploy their solution on. So that's sort of one problem. The second problem that we see people running into is how do they scale their problem, either on a single processor, so that's how can you be more effectively utilizing, say, multiple cores on a single processor, or how do you go from a single processor to multiple processors without getting, say, lost in communication or other types of bottlenecks that are very easy to run into. And so when we look at sort of the three techniques that people use to do this optimization, there's three things that you often see people doing. The first is on data IO. So this is, hey, I'm going to change the way my data is organized. I'm going to write a fast data loader. I'm going to change the formats to maybe help me optimize or tune. The second thing you might try to do is compute optimizations. So this is, I'm going to buy new hardware, right? To get more hardware capabilities. I'm going to change the way I launch my processes. I'm going to update my math libraries, maybe my compilers, or I'm going to change my framework capabilities themselves. And then certainly a third, but certainly important factor is on, especially when you're going to the world of distributed scaling, is how do you manage your communication? And in order to manage that, what people often do is work with the network hardware. So there are different types of hardware that you could buy that might improve your communication, say throughput or latency. There are different network protocols you could use, different communication libraries, different algorithms, and deeper integration of these communication algorithms and libraries with some of the frameworks that are being used by compute. So just to very specifically, if you're using, say, distributed PyTorch, you might have a choice of communication libraries that you could use. And so integrating the right communication library with the right development environment becomes very, very important. So I'm going to talk about just one example over here as something that we've been doing, and this is under the compute part and compilers specifically. So when we think about how would you optimize a neural network performance with compilers, let's take a look at what happens in when you type code in TensorFlow, and from there to it running on your processor, what's actually going on. So we'll just take the sort of left branch, but it's about the same for the right side as well. So you take your code, you've written something in TensorFlow, and you're going to have it run. So you're going to have it compiled. What TensorFlow is doing is typically generating some sort of a graph under the hood that's then passed on to a library called XLA, which stands for the Accelerated Linear Algebra Library, which then creates an optimized, high-level optimized intermediate representation. So this is still sort of in the world of TensorFlow. That IR, or that intermediate representation, is then converted into an LLVM compatible intermediate representation, say for the CPU. It might then go through some sort of an optimization step, which then creates an optimized intermediate representation, and that's what's actually run on your end processor. So that's sort of the steps your code takes, if you want to call it that, from you hitting run and it being executed on the CPU. And if you look at the right branch of this, that's what would happen for a GPU. So it's about the same. We've certainly skipped a couple steps here, but this gives you a rough idea of what's going on over here. So in this case, what XLA is doing is right at the top is essentially inserting calls to parallel libraries. But what we found in our testing is that it really struggles to optimize parallelism. So when you run this, let's take the case of a CPU, we find that the utilization of the different cores is a lot lower than maybe we would be able to do. And so what we've done, and this is joint work with some folks at the Computer Science and AI Lab, is actually integrate a new compiler called Taper into that, integrating that with LLVM. And integrating this whole package into the XLA framework. And so what Taper does, and there's a paper that's cited at the bottom that you're welcome to go and read that has more details about this. But what Taper does is it does a better job of understanding parallelism and is able to optimize all the parallel code together. And it's able to also optimize code for the target hardware. So how you might parallelize your code for a CPU is very different than how you might parallelize it for a GPU. And so it's aware of differences in hardware. And it allows us to build new parallel libraries using this Taper representation. So you might say, okay, that's kind of cool. Like, does that work? Well, it turns out that it does actually work quite well. So what I have over here is a series of results. Again, the paper that I've cited below has a lot more details. But if you look at what's going on, so this is across 4 different hardware platforms. The blue line, the blue triangles are sort of with the library, and the green triangle is sort of native. This is just Google's XLA. And so we see in almost all cases, or in every case across these different hardware platforms for a convolutional neural network, we're able to see a significant increase, which is in the throughput of the number of images per second. And in fact, if you look across different CPU architectures, we're able to see almost a 30 to 100% speed up across a lot of these different platforms. And I think the most exciting part of this is that this is essentially for free. This is just changing so this is, the user is agnostic to this. All we've done is change the compiler under the hood, and you're able to see some pretty significant speed ups. But all this is really good for a single processor. So if we were to look at running this across multiple processors, you'd need to do a lot more stuff. So in the case of data distributed training, which in the interest of time here, I'm just going to hope that many of you are familiar with, we're basically doing, processing replicated models and then doing some sort of parameter update. What we're able to do is, on our supercomputing system, is enable a lot of these libraries to have some pretty nice speed up and scaling across these. And so what we have over here is just a very simple result of sort of the performance our team has seen compared with, say, something like the NVIDIA DGX or Oak Ridge National Lab Summit system. And the reason we're comparing is, we have a couple of critical differences. First of all, we use gigabit Ethernet interconnect, which is a lot slower than a lot of the sort of big high performance computing systems. And also our node density is a lot less, in which we have only 2 GPUs per node, rather than, say, something like Summit, which has 6 GPUs per node. And so this is pretty cool that we're able to get these libraries that scale, as well as some of these other, folks like Oak Ridge and NVIDIA are very well, are highly capable players. And so we're very happy to be able to be within the same realm of performance. But all of this testing is on data distributed parallelism, which isn't all that interesting. And so one of the postdocs in my group has been doing a lot of research on, what can we do to go beyond data parallel distributed learning? And so when we think of a neural network, right, and considering, say, a feed forward neural network, the information travels sequentially through the network. And so through forward propagation, you're setting neural states, and through back propagation, you're typically updating the weights and biases. And a lot of this speed up is limited by serial execution. For those in the audience who are familiar with Amdahl's law, you'll know what I'm talking about. And so we have some research going on here on, how can we increase parallelism by solving for these for weights in layers concurrently. And this is something that we've applied to residual networks, or ResNets. And so what we've done is we've treated the forward propagation through a ResNet as a discretization of a time-dependent ODE. And again, we have a paper on this. It actually won an award at a conference. So I encourage you to take a look at that for some of the details. But the intuition is this: if we look at the plot on the bottom right, we're able to take like a pretty deep ResNet, and then, thanks to the structure of ResNets with these skip connections, we're able to utilize a technique called multigrid, which is pretty popular in numerical analysis and applied extensively in the world of computational fluid dynamics, to basically concurrently solve for different subsets or blocks of layers within the ResNet at the same time. And so this is really exciting. This means that I could, in a time parallel way, solve different parts of the ResNet simultaneously. And the other cool thing is you could actually use this in conjunction with something like a data parallel approach, like I showed a couple slides ago. This is work in its early stages, but we're able to see some pretty significant speed up. Again, in the interest of time, I'm just going to jump to the main thing, that this technique works well, especially in very, very deep networks, and with millions of parameters. And we're able to see speed ups of the order of 10x when we distribute it to, say, 64 GPUs. And again, as I mentioned, this 10x can be in addition to whatever you are going to get from a data parallel approach. Now, this is still early work, and what we're finding is that we are limited very often by the communication overhead. And so that's why this works really well for very, very deep networks where each processor is working on a pretty sizable chunk of the problem. But certainly if you had a smaller hardware platform, this would actually probably perform much better. So, okay, with that, I'm going to jump into data conditioning, and I think I am going to move through this relatively fast. So we've seen a lot of people spend a lot of time on data conditioning. So this is like, how do you store your data? What do you do with the data? How do you apply labels to the data? And so something that we've been doing is building a new tool called Big Dog, which is short for the Big Data Working Group, which is a new approach to integrate different types of databases. And again, this is open source software. You're welcome to try downloading this and playing with it. We have, like, again, a lot of write-ups if you're interested in more of the details of what's going on in this. But so this is Big Dog is sort of our approach to, how do we get people to think about disparate data and how to integrate them. And so we have a number of foundational operations in this. The first is a common interface. So you can build your visualization clients or applications through this common interface, talk to a multitude of different databases. We've been building what are called analytic translators or shims. This allows you to, through this common interface, talk to different database engines that might speak different languages. We have data translators to move data across different database engines and support for different data via islands. So rather than really going into more details about what's going on, it might be helpful to just show you a brief demo of what happens in this. So let's take an example of autonomous vehicles. In the case of autonomous vehicles, this really struggles with the heterogeneity of data. So for a given vehicle, you may have different sensors collecting data with different modalities. So you might have, say, time series GPS, you could have video, you might have text labels, etc. And so here's just a simple demo, and I hope this video is able to play, of being able to run Big Dog, taking this disparate data, storing them in different database engines, and being able to run something like this Big Dog database engine, and how it makes it easier to write analytics. So we have data collected here in Cambridge, Massachusetts, and we have somebody that's trying to write an application. And in this application, what they're trying to do is basically do queries by different types of objects, which has come off of an object filter, apply an object classifier run on video. They're trying to look for different types of events and locations. So these are like different modalities of data that are out there. Right. Okay, so a user can kind of go in here, hit queries, and this is now sending different parts of this query to different backend database engines in order to get results back to the user. So in this case, they're looking for a person in a bus near a particular location. Now, since we have this data stored within these different types of things, we can quickly switch to a view which has mapping infrastructure. So what we're looking for here are stop signs and traffic lights at different locations within the city, and this is sort of around MIT's campus. And you can finally use this to basically look across your data set, and what we found is that people being able to use this under the hood, you're able to reduce the overall time it takes to write your analytics because the data is sitting in the right spot and you now have efficient access to different components of the data. All right, so one thing in particular that we've seen has been troublesome is video data, right? As I mentioned over here, what we did is we ran our video that we collected off a dash cam, ran that through an object detector, and then stored those text labels in a database. But what if you didn't want to do that? And so in many cases, people are collecting massive quantities of data, and there are limited options for how you index and search through this data. And so some specific challenges that people run into are, object detection is pretty expensive. So if you take like an off-the-shelf model like YOLO, these things are actually pretty computationally heavy, so tough to run it across, say, a fleet of vehicles simultaneously. You're also then limited to searching for objects which the off-the-shelf detector has in it. So maybe I can only look for traffic lights, but I can't look for, trees that have yellow leaves on them, right? They may not be there. And then there's this other huge challenge of distinct object indexing. So in the example we have here, that traffic light should be indexed as the same thing, although it shows up in 2 different frames. And so in order to address some of these challenges, we've been building a tool called ExSample, which is a new type of database that's good at searching and indexing a video, and it does it through adaptive sampling. So I'm going to give you a little bit of insight of what's going on here. Again, this is a really high-level view, and please email me if you'd like to see the paper that describes this in a lot more detail. But the basic idea is to apply adaptive sampling to portions of video that are likely to contain objects of interest. So how do we do this? And this is shown graphically at the bottom. The first step is we take our big video, which could be tens to hundreds of hours, and we chunk them into smaller pieces. And then we score these chunks based on the likelihood of consisting of an object of interest. And so in order to do this, you see sort of the equation at the bottom. We basically parameterize a gamma distribution. And so the first part of that gamma distribution, the first parameter, is essentially the number of instances that have been seen before. And the second is the number of samples that have been processed from this chunk. And essentially where that falls into the gamma distribution gives you an approximate score for what that jth chunk would be for that object of interest. Then based on that, we can select or sample a frame in which the a chunk in which the score is higher. We can read the frame, do object detection, look for duplicates, and then update the chunk score. And so doing this, we can look for objects of interest pretty quickly. Now, this can actually lead to huge performance benefits. So here's some results that we have of using this technique. In the query that we run here is find 50% of the instances where a particular object exists in a frame. And so the object is given in the sort of title below the plot. And the y-axis here is the number of minutes. Up is bad, down is good. And so we have 3 scenarios from 3 different types of cameras. The first is an indoor static camera. The second is an outdoor static camera. And the third is a dash cam, a car mounted dash camera. And in every one of these cases, we're able to see some pretty significant benefits in, almost order of 7x improvement. And so this is really early research, but this adaptive sampling technique can lead to some pretty significant time savings when you're searching, say, through video feeds for something of interest. So you could imagine this could be really useful if you had, say, hours and hours of video at home that you'd like to search something through, or maybe someone's looking at surveillance camera footage and they're looking for something of interest. This makes things a lot easier. Some of you who are paying attention in the last slide might have noticed that we're still using an off-the-shelf object detector. So we're still limited to classes which exist in an off-the-shelf object detector. And so what we're currently working on is how can we leverage reinforcement learning in addition to the adaptive sampling technique I just mentioned, in order to look for really any sort of data. So here's an example. I'm taking data again from the autonomous vehicle dashboard camera, and these are just 9 example frames from the video. So this is what you'd expect to see from a dash cam on a car. Now, what we're going to do is we might be looking for something like a person wearing a backpack, right? Maybe that's the query that I have, but I don't know where that is in my data set. So what we can do is just download data from a place like Google Images, just search person with backpack on Google Images. We downloaded the first 10 examples that are there. And we're going to essentially use this along with our adaptive sampling to look through the video data for this. And so in the first round, these seed images kind of help us get a few things, but not too many hits. So now what we're going to use is reinforcement learning. So we're now going to select the ones that are relevant to us, help that update the model, and you can see immediately we're able to look through these hundreds of hours of video and finding people with backpacks much, much better. This is an example. This is obviously research in progress, but this is a type of work that we're trying to do when we talk about AI enabling data. So you can imagine this would be your data conditioning step that we're trying to help people with, right? So through your hundreds of hours of video, maybe I'm just doing a classifier on the types of people that are there. And so we can use something like this reinforcement learning tool to help select parts of the data that are more interesting and valuable to people as they go on. So, all right. So with that, let me just jump into really quickly a little bit of the work that we've been doing in the area of distributed algorithms. So I'm sure many of you are familiar with this, but in general, and again, kind of say this in general, larger DNNs, so that means neural networks with more parameters, tend to perform better. And so if you look at the plot at the bottom, this is a plot of the ImageNet Challenge winners from 2010 to 2017. And basically it shows that as the top 5 error rate goes down, we're starting to see sort of this growth in the number of features and layers associated with the sort of winning entry neural network. Now, one of the challenges is that we have limited memory and compute. And so what we're looking at building are applications that exploit sparse and distributed algorithms more efficiently. So on the right side, we have an example of a dense network, and there's different ways, such as pruning or sparse training, that you might be able to actually construct a sparse network, which is far more space efficient, but maybe doesn't compromise too much in terms of accuracy, or there isn't too big a accuracy degradation. So there's been a lot of work in the world of sparse processing. So here's an example of some work that we've done on my team to actually help build out sparse neural networks on a popular database called Redis, which is an in-memory database. And in order to do this, we integrated a standard called the GraphBLAS along with Redis in order to speed up some of this processing on conventional hardware. And so we're able to see some pretty significant performance benefits. So if we look at the right side, this is just a simple graph algorithm. So what we're doing is a matrix vector operations shown at the bottom, which actually translates to a breadth first search, or a one-hop breadth first search in a graph. So the kind of figure at the bottom shows the duality between the graph representation and the matrix representation. And so what the plot that we have on the right is the performance of Redis graph, which uses this sparse matrix library under the hood called GraphBLAS, working and compared across a number of other pretty popular graph databases. And we're able to see some very significant performance improvements. So you can imagine that this tool could help you if you're trying to build a sparse neural network. And as I showed earlier, a sparse neural network can be written back down as a series of matrix vector operations. You could use something like Redis graph in order to speed things up, especially if you're using one of these other popular technologies to store and process your data. We've applied a lot of this research to video analytics and video action recognition. This is actually work done by one of my students who won an award for his thesis on this work, but being able to map this efficiently to different types of hardware platforms, figure out what are some of the scaling and computational bottlenecks, and then to train some of these networks and actually make them available. So if anyone's working in video processing, let me know. We've open sourced a lot of these models, and you can actually, we've created a model zoo that you can go and download these and use these for your video processing problems. We've also applied these to a series of different applications, such as network anomaly detection for cybersecurity. And again, these techniques that we've talked about from the AI enabling capabilities used on this, we've seen some, we've been able to quickly reduce the amount of time taken to build these machine learning and AI models, and then we're able to actually get good science out of a lot of this work that we've put together. So, what we have over here is the usage of the sparse and distributed computing tools that I talked about earlier for network detection. And we've used this on an open source data set called Maui, and able to see some pretty good. So this is one of the early works on, how do you classify a type of network attack that might be occurring on your cyber network, which I think is really fascinating. Again, a lot of this is work in progress, and so there's a lot of places that we can go from here. But the enabling capabilities that we've been building help us really build these pipelines as quickly as possible, so we can spend more time on getting the right model, being able to figure out, what types of model architectures to use, rather than, fooling around with the data and, how do you organize the data, where do you store it, that kind of stuff. So with that, I know I ran through the last few slides, but I did want to save some time for questions. And so with that, I'll thank you once again, and I'm available to answer any questions.
Hey, thanks, Vijay, for your really interesting talk.
I have a question.
Yep.
Did you use gpipe for parallelization? You didn't mention that how you just remove the dependencies between the likes of ResNet.
I'm sorry, did we use which one? I didn't hear you there.
gpipe, Google pipelining method, because as I understand, that was a pipelining parallelization.
You're talking about the work we were doing on the ResNet?
Right.
Yeah, we actually wrote the entire thing from scratch. So that was all written in CUDA. And so we actually wrote that entire thing from scratch. We have not integrated that with any of these other pipelines yet, just because getting the math right was a significant challenge for us. So I didn't go into too many details, but we essentially borrowed a technique called multigrid, which is used in the numerical analysis community, which allows you to, so if you can set up your problem, which a ResNet actually sits really nicely as an ordinary differential equation, you can actually use this sort of time parallel technique. So a lot of the challenge that we had was on getting the algorithm to get the correct output. So we needed that level of control on what essentially part of a GPU was working on what part of the problem. So we didn't use those libraries yet. So it's all written from scratch. But yes, eventually we would like to get it to a framework like that.
Okay, cool. And I have a question about your computer vision part. Did you use YOLO or something like that? Because I guess they have right now the best real-time response.
Yes, that's right. So for the off-the-shelf object detector where we're using YOLO, we've also tested with a few other off-the-shelf object detectors. For the reinforcement learning part, no, we did not, right? We were essentially using some seed images to create our own thing that we could search through the data. But for the first part where I showed, looking for a person or a car in the static and the dash cam video, yeah, we used an off-the-shelf detector like YOLO. And our biggest contribution was, how do you pick the part of the video that's likely to have that object of interest? And that was sort of the big contribution, not the actual object detector or classifier part of it.
I understand. Thank you.
Sure.
This is Wayla from audience. So it's a great talk. I have a questions. In one of your slides, you mentioned about the communication overhead in some GPU scaling algorithm. Can you talk a little bit about that? What library did you use for GPU communication, and why that is a limiting factor for your implication?
Yes, so let me see if I can actually jump back to that slide. And I think Beta also had a question on the same piece. All right, so I think this is the slide that that you're talking about. So I think, as I mentioned over here, we used CUDA streams. So that's the communication library. We used CUDA streams for the asynchronous execution, and then cross processors, we used MPI for the actual communication. Let me sort of give the intuition of where we ran into a bottleneck over here. So when you take this ResNet, let's say you have 150 layers, right, which is a pretty popular size of ResNet. And if you start to chunk that up across GPUs, right, so you're taking some subset of layers and mapping those to different GPUs, it turned out that a lot of the time was spent communicating across the GPUs. So the actual GPU would be able to do their updates on their small part of the model pretty quickly. But when they were trying to communicate with each other to do this, so I didn't go into too much detail here, but there's a technique called multigrid. It's sort of a two-step process. You do what's called F relaxation. So you you break your model up into smaller chunks, each one in a time parallel way. So in parallel, basically, each one is making updates, what are called fine-grained updates to the local part of their model. And then at a certain step, you do what's called a coarse-grained update, which sort of gives the error, and then they kind of follow that sort of fine-grained update once again. So it's in that process where you do that coarse-grained correction, where all of your GPUs now need to transfer what their output of the fine grain was to the next GPU. And so if you have really small model updates going on a GPU, you end up spending a significant amount of your time in that communication process. And so for us, we used MPI, and as I mentioned, we have 25 gig E as the interconnect. We do not have NVLink, which could have possibly improved the performance. So everything was going back through the host CPU and then to the other GPU. And we only have 2 GPUs per node. So again, if you had 6 with NVLink, you could possibly see an improvement over there. And so what we were running into, so when the compute to communication ratio is higher, what that means is each GPU has to do a lot more crunching before it actually has to communicate. We're able to see these speed ups become much larger. But when we have smaller model, and that's why the result I'm giving you here is for a very deep network, right? 4,000 layer network with 2 billion parameters. So that means that each of the GPUs was doing a pretty significant amount of compute before it needed to communicate the parameters. Because again, if you're trying to communicate 2 billion parameters, you want to do that as rarely as possible. Does that sort of answer the question that you had?
Yes, that's perfectly answered, because we also ran into the similar case when we partition the data into lots of GPUs, then the communication becomes the bottleneck.
Exactly,
So
exactly.
Yeah.
And now, what do you use for like, do you have NVLink or some, an InfiniBand type interconnect, or?
Yes, we run our model on Summit, so that has NVLink between every three.
Okay, you're on Summit.
GPUs.
Okay, yep, familiar with that.
Yeah.
Yeah, but exactly, you'll run into that at a different number, right? We might have run into that at 4. You'll run into that at 6 or 12 or something like that.
Yes, quite similar, but it's not on the machine learning models, but this physics model. But it's quite similar. We end up later use a subbrain communication. So essentially, we partition the data in a smaller subset of GPUs, and then for each subset, do some computation, and later at the end, and do the communication.
Yeah, that makes sense. That makes sense. So yeah, so some of this work, just to kind of close the thought here, some of this work is early. Certainly for the very deep networks that we're starting to see, especially in the world of like NLP. And by deep, I mean just large networks, right? Billions of parameters is not uncommon now in some of these NLP models. This kind of process could work well. We're still investigating other areas. It turns out that the ResNets have the best mathematical, have the best conversion, as I mentioned, to an ordinary differential equation form because of these skip connections, which allow us to sort of break them up very neatly. But we're trying to see if there are other model architectures that we could apply this to.
Okay, thank you.
Sure.
Do we have more questions for Vijay? If not, I will ask him a question we asked most of the people giving a talk, and I think you are more from the HPC computer science area. So we asked most people from this community how or which aspects of high performance computing should the AI community use, and what can the AI community learn from things in computer science which are there for a long time.
Yeah, so I think that if I think about one of the biggest opportunities as an AI researcher, and with some of the projects that we have, a lot of it is on this upfront data cleaning and data curation part of it. So I think it's sort of a thankless job, but just people are spending a lot of time on. So I think there's a lot of great opportunities there. But again, putting my more traditional high performance computing hat on, I'd say the divergence of hardware is becoming a major challenge. When we used to do supercomputing, like what I want to say a long time ago, but we're talking less than 10 years ago, it wasn't uncommon to have a single processor type on a single system. We now have about 6 to 7 different processors on a single system. And so we've been doing a lot of research on, how can we effectively map people onto hardware and help take away those choices from the end user, because a lot of people aren't aware. I showed that plot earlier, which had sort of the gigaops per second versus the power utilization. That's a really difficult chart for people to understand, not because they're not able to, but it's because they shouldn't have to. If you're a domain scientist, we don't want you focused on computer science. You should not have to spend time doing that. And so I think it's on folks in the computer science, high performance computing world to make these tools as easy as possible, so people don't need to learn about computer science in order to get moving. Because I think there's some, we're seeing this all the time, right? Applying deep learning to different types of problems, or applying artificial intelligence techniques to different sets of problems, in mechanical engineering, chemical engineering, and name your topic. And there's just so much that you could get. We don't want people fooling around with how to install TensorFlow, how to get TensorFlow to run faster. That shouldn't be something that a physicist is worried about. That should be something that folks like me that run these large supercomputing centers need to be worried about. So I don't know, Patrick, if that addresses your question, but just a few thoughts that I could think of, at least what I have my group focused on right now.
Yes, thanks. It was really interesting because we asked a lot of people what they think what both communities could learn from each other. And yeah, it was a quite nice statement. And thanks again for your talk. We are close to the hour, so we're wrapping up.
Okay, thank you. Bye-bye.